Finally, I'd like to give another brief discussion about not just the types of integrals we've seen in this class, but the relationships between them. Let's organize these a little bit. So we've got theorems about integration that say we can do an integral of something, or we can do something on the boundary. It converts between points and curves, curves and surfaces, or surfaces in three-dimensional regions. Let's write down what all of those are. We've got integration theorems in 1D and 2D and 3D, and some of them convert between points and curves, some of them convert between curves and surfaces, and some convert between surfaces and solids. And some of them don't make any sense. There's no two-dimensional regions in 1D and no three-dimensional regions inside 1D or 2D, so we can leave those out. When we look at the top row is basically the fundamental theorem of calculus. We've got the regular fundamental theorem of calculus that says that integrating a derivative is the same as evaluating at the end and subtracting the value at the start. That's relating an integral over a one-dimensional region with an integral on the boundary. And in the line integral case, we can say if we're integrating a gradient vector field where we've got a potential function, then we can just evaluate the potential function at the end and the potential function at the start. For converting between 1D and 2D, inside two-dimensional space, we've got Green's theorem that says that the double integral of curl is the same as the single integral of our original vector field around the outside boundary. And in 3D, we've got Stokes's theorem, which says that the double integral of curl in 3D is the same as the line integral of our original vector field, again, around the outside boundary. And for converting between 2D and 3D, we have the divergence theorem, which says that the triple integral of divergence is the same as the double integral of our original vector field around the outside surface. That kind of systematizes this, and it's part of a pattern. We can see a pattern in what's going on. We've always got a conversion process that goes between boundaries and regions that they surround. It always kind of has some kind of operation that changes between, something in one dimension and something in the next dimension where we're integrating it. But it's all organized for this class in terms of these. If we wanted to talk about integrals in 4 dimensions or 5 dimensions or so on, this table would get bigger. We'd have more things to say, and that becomes important when you have extra variables like time. But for us, this is the main of what we're working with.